Okay, so now that we know the formal definition of a limit, or the precise definition, how can we use it? Well, one thing we can do is to look at this definition on different graphs, and that's what we're going to do here. We are going to use this graph to find a delta greater than 0, such that the definition of a limit is satisfied. So the absolute value of x minus c is less than delta implies that the absolute value of f of x minus L is less than epsilon. Okay, and they've given us some different things here. We do know our function. It's the line 4x minus 3 in this case. We know the c value that we're looking at is going to be 5. Okay, the limit, all right, the L value, this L equals 17 here. This is the limit as x approaches c, which is 5, of our function 4x minus 3. Okay, which you can verify with direct substitution, right? Plug in 5, you would get 4 times 5, that's 20, minus 3 gives us 17. So yes, that is indeed the limit. All right, we are just now going to find a delta value to go with this epsilon that they've given us. Okay, so they tell us that the epsilon we're given is epsilon equals 0.6. And recall, that is setting off a distance or an interval along the y-axis. And we're going to be within that distance of the limit, 17, as long as x is within some interval along the x-axis, within that interval, within that distance of c, which equals 5. Okay, so zooming in on our y-axis here, you can actually see epsilon at play. Okay, they're telling us this top value here is 17.6. Notice that that is literally L plus epsilon, because 17 is our L value, epsilon was 0.6, so that top value is L plus epsilon. Same type of thing along the bottom here, 16.4, that is L minus epsilon, 17 minus 0.6. Okay, so we want to find the delta value, the value for that x direction that will guarantee us to be within this interval of y values. All right, so let's go look. Notice how they've used these nice hash marks to show us where things are lining up on the function. Okay, and then we're going to go down in the x direction, and we see here that we have our c value of 5. 5 equals c. There we go. Okay, c equals 5. All right, so then we have to see what the boundaries of this interval on the x-axis are. Notice that the upper one is 5.15. That's going to be our c plus delta. The lower will be our c minus delta. Okay. Remember, based on that picture that we drew before for our definition, it's right up here. Okay, so we're looking at this part of things right now, c plus delta being the upper boundary of that interval, c minus delta being the lower boundary. So if we know that c is 5 and we have these two values that we know to be c plus delta and c minus delta, we got to calculate delta. And you can see here, I think it's easiest to look at the upper value. Delta is going to be that 0.15 that gets added on to c. Okay, so delta equals 0.15. Because Yeah, that would make 5.15 truly C plus delta. And then 4.85, that's 5 minus 0.15. So that really is C minus delta. Okay, and for this problem, that's just our answer right there. Delta is going to be 0.15. Okay, there's our value. Okay, so we've found this delta value. Notice how we did use the positive result for that. We didn't say delta was like negative 0.15. Now, we assume delta and epsilon are positive by default. So we found that, and this guarantees us that as long as the distance between x and c is less than 0.15, that means x being in this interval here, okay, that will imply that the distance between f of x and L is less than 0.6, which would be this interval right up here. And we can see from the graph that that is true.